The blast furnace. The heart of the steel plant is the blast furnace, a giant tower of the fire and chemistry. Here, iron ore, coke, and sinter descend from the top, while hot air blasts from below. Temperature soar beyond 2000 degrees Celsius. Coke burns, generating carbon monoxide, which reduces iron ore into molten iron. In the blast furnace, iron ore is reduced to molten iron through carefully arranged layers. At the top, we charge alternating layers of iron ore, coke, and limestone. The coke acts as a both fuel and reducing agent, while limestone helps remove impurities. As hot air is blasted in from the bottom, the coke layers burns, creating intense heat and carbon monoxide gas. This gas rises upward, reducing the iron ore in the layers above. Meanwhile, the limestone layer decomposes, forming lime that reacts with silica and other impurities to create molten slag. At the bottom layers, molten iron collects beneath the slag, ready to be tapped out. Together, these stacked layers, ore, coke, and limestone, form a continuous cycle, ensuring efficient smelting and separation inside the furnace. A river of fire flows, carrying the promise of steel. Steel melting shop. Hot metal alone is not steel. It is a brittle, impure, and carbon heavy. To refine it, we enter the steel melting shop. Here, the basic oxygen furnace awaits. Oxygen is blown into molten iron, burning away excess carbon. The fiery roar transforms pig iron into liquid steel. In steel making, the basic oxygen furnace or BOF is where molten iron is transformed into steel. The process begins when molten pig iron from the blast furnace is poured into the BOF vessel along with scrap steel for cooling and recycling. Then a water-cooled oxygen lens is lowered into the furnace. Pure oxygen is blown at supersonic speed onto the molten iron. This oxygen reacts with carbon and other impurities, forming gases like carbon monoxide and oxide that escape or combine into slag. Within about 30 minutes, carbon content drops dramatically, turning brittle pig iron into strong low carbon steel. Finally, the slag layer is removed and the purified steel is trapped out, ready for casting into slabs, billets, or sheets. This rapid BOF process revolutionized steel making, producing high quality steel efficiently and at massive scale. After steel is made in the basic oxygen furnace or electric arc furnace, it still contains unwanted gases and impurities. That's where secondary refining comes in. In this stage, molten steel is transformed to a ladle furnace or refining vessel. Here, argon gas is bubbled through to remove dissolved oxygen, nitrogen, and hydrogen. Fluxes are added to capture sulfur and phosphorus, forming slag. Precise alloying elements like chromium, nickel, or vanadium are introduced to achieve the desired grade of steel. Temperature is carefully controlled and the composition is fine-tuned. By the end of the secondary refining, the steel is cleaner, more uniform, and ready for casting into slag, billets, or sheets. This step ensures high quality steel for everything from cars and bridges to household appliances. Secondary refining, ladle furnace, vacuum degassing, alloying elements added manganese, chromium, nickel to create different grades. Casting the steel. Liquid steel must take shape. Continuous casting machine solidify into billets, blooms, and slabs. Imagine glowing rivers of steel cooling into solid blocks, the raw forms that will be rolled into products. After secondary refining, molten steel is ready for solidification. This happens in the continuous casting machine or CCM. The steel is poured from the ladle into a tundish, which acts like a reservoir, ensuring a steady flow. From the tundish, liquid steel enters a water-cooled copper mold. As the steel moves downward, the outer shell solidifies while the core remains molten. To prevent cracks, the strand is continuously sprayed with water. Rollers guide the semi-solid strand, bending it into a horizontal path. Finally, the continuous steel strand is cut into slabs, billets, or blooms of required length. The CCM process is fast, efficient, and ensuring uniform quality, making it the backbone of modern steel production. Remaining process will be continued in the next video.